Thank you very much for the kind introduction. Thank you very much for the invitation. It's really exciting to be here today and share with you some of my research topics. What I'm going to try to cover in the next 45 minutes are basically two topics. And with these two topics, we try to tackle two respective challenges that the modern AI or deep neural network face. So the first challenge being that the neural networks tend to be over-parameterized, meaning that the neural network have actually more parameters than it is necessary for them to have to model a certain set of data. And this kind of over-parameterization often leads to then the lack of robustness of the model, leads to the lack of generalizability of the model and many other issues. So with the trick or with the technique of tensorization, we try to tackle, to minimize the risk of this over-parameterization. That would be the first part of the talk. In the second part, I'm going to talk a little bit about the uncertainty quantification in deep neural networks, because as we know, neural networks are really not that good at quantifying and expressing uncertainties. Even if they do, they tend to be either over or under confident about certain predictions. So what I'm going to talk about is how to combine a very classical machine learning model, which is a Gaussian process, with deep neural networks. So starting with the first topic, tensorization of neural networks in deep learning, what it actually means is, well, the basic idea is, can we find a way to represent large weight matrices in neural networks with S product of smaller tensors? So what I mean by that is the following. So here we see we see that quite often nowadays. This is just a dense layer or fully connected layer. This is the most intuitive and the simplest building block within a neural network. And what it models is such a mapping relation from an m-dimensional input space to an n-dimensional output space. And the parameters that are necessary to perform this kind of mapping can be represented with this matrix of dimension n times m. This is very intuitive, very simple, but the problem is this is also quite often the heaviest part within the neural network that we can think of, because we need so many parameters. Before deep learning, in the early days of neural networks, there was a simple trick to compress this kind of fully connected layers, which is what we see on the right-hand side. So what changes here is that we can build a intermediate low dimensional layer without any activation, without any nonlinear activation. And by doing so, what actually happens is that we decompose the entire fully connected layer, which is we decompose this full matrix as the product of two smaller, much smaller matrices. So here we would need n times m parameters. Here we would only need n plus m multiplied by r, so many parameters. So this is a very simple trick in the early days of neural networks. It never became really popular because here we introduced this bottleneck architecture, meaning that we have to enforce that the neural network can compress all the information from this layer into this layer. And sometimes the model can really suffer in terms of expressiveness. So if the model cannot find such compressed formulation of the data, then the performance and the expressiveness of the model will suffer. So but the reason that I'm showing this as a motivating example is that with the trick of tensorization, we simply follow this idea, which is how can we find a more efficient way to represent this full matrix. And now in order to talk about and to work with this so-called tensorization, I would very much like to introduce, and of course, for those of you who are already familiar with this topic, to recap the idea of the so-called tensor graph notation. So in this tensor graph, we can see the tensor graph notation as the language of high-dimensional tensors. So there are two basic vocabulary in this in this language, which are the nodes and the edges. So with node, we represent a tensor with an edge that comes out of the node to represent the mode or the dimensionality of that tensor. For example, if we have one node without any edge coming out of it, we mean with this notation just a scalar, which is a tensor without mode. If it has one edge coming out of it, we have a one-dimensional vector. If we have two edges coming out of it, we mean with that a matrix. We have three coming out of this, we have a three-dimensional tensor in strict sense. But just like any languages, so the language is not that interesting unless we can make sentences out of the vocabularies. So the sentences that we can make out of these notations are what we call tensor contractions. So these are the operation with which we combine and merge multiple tensors to formulate new tensors. So here we can, we see an example here. Here we have, in this notation, we actually see two nodes, A and B, and we see that A and B both have edges coming out of them, meaning that A and B are both the vectors, but they share this edge here. And this operation tells us that what happens in this tensor contraction is that we calculated the sum of all the components in tensor A and tensor B over the mode or over the dimensionality that they share. So in matrix notation, what happens is just to calculate the dot product between these two vectors. And now if we imagine A and B are both matrices, so they have two edges coming out of those. So if we merge these two tensors, we contract those two edges, tensors or matrices over this edge, meaning that this edge will disappear. So the outcome of it, if we denote that as C, then we have another matrix, because if we look at the C as a whole, it still has two outgoing edges here. And that, of course, it might also happen that we try to contract two three-dimensional tensors in strict sense over two edges. And now we realize that this could be really challenging and difficult and complicated if we try to express that using the matrix notation. So the second the second set of tools that I would like to introduce is the so-called Einstein summation notation, with which we can express these high-order tensor contraction in a very simple way. So what the Einstein summation notation tells us is that we can actually write any kinds of tensor contraction operation simply by writing all the tensors one after another, completely ignoring the order in which we write those tensors. But we follow the rule that if so first, the following two rules. The first rule is that we have to emphasize, we have to express that the mode, so the dimensionality of each tensor using the indices. If we write A with a subscript or with as a function or whatever, if the n here represents the mode, meaning that here we have only one index, meaning that this is a vector. If we see something like A, M, and N, meaning that here we have two indices and A would be a matrix. So this is the first rule to denote the mode of the tensor. The second rule is that in such an equation, in such an operation, if there's one index that appears more than once, then that is the mode that we are going to merge to contract these two tensors with. So this is the mode that is supposed to disappear in the tensor graph notation. For example, here what we see is actually a matrix multiplication. Here A has the indices M and N, B has N and K, and here N appears twice, meaning that we can contract these two matrices over the mode of N. So what remains in terms of the indices are actually M and K. So M and K would, the modes of M and K would remain. And with this Einstein summation notation, we'll be able to express this complicated tensor graph notation in a very concise way. So here we have M and K, and here MKR. So obviously the M indices M appears twice, and the K appears twice. What remains would be the indices N and R, and therefore the most that remains is actually the N and R. And the reason that I introduce these two sets of toolbox is that there is actually a one-to-one, a unique mapping between the tensor graph notation and the Einstein summation notation. We can express any tensor graph notation, we can express any tensor contraction that can be expressed with a tensor graph notation in with the Einstein summation notation. And the Einstein summation notation is well represented and is actually implemented in a lot of libraries, for example, in NumPy, for example, in TensorFlow, for example, in Torch. So here I've provided some examples how to implement the Einstein notation on the left-hand side, which is actually exactly, almost exactly how we write it. So the torch Einstein function has actually two groups of input. The first is the indices that is supposed to be contracted, and the second group will be all the tensors that we try to contract. And here would be, so this operation is exactly the same as calculating the inner product. And if we write it Mn and Nk, on the other hand, the output would be Mk, meaning that we calculate the matrix product of these two tensors. And of course, the same applies to that. So this is only a recap or preliminary about the toolbox that we need. The true reason that we are interested in that is how can we use that to formulate very complicated ways to decompose the weight matrices that are expected to be large in a neural network. But let's first start with the simplest one. So here what we have is a very simple fully connected layer, y equals wx. And if we write it down using the tensor graph notation, we see that, okay, obviously M has two dimensions, the X has one dimension, and in the graph notation, what happens is that this mode of M is supposed to disappear, and the outcome will have a dimension of N. So the number of parameters that we would need is N times M. And this bottleneck trick that we have just seen can be also expressed in a similar way. So in Einstein notation, we have X, we have the first layer and the second layer of these fully connected layers. And what happens here is really similar. The first thing would be to contract X with the V, and the second step would be with U, and so on. And like I said, this bottleneck has the challenge that we have to somehow compress all the information over this mode or over this edge of M. So that brings a lot of limitations, and that is somehow the reason that this trick never became popular. But in the year of 2015, Novikov and his colleagues came up with a very brilliant idea how we can improve on such simple architectures. So the idea is the following. If we can formulate the input, namely this X, which is originally a vector, as a high-dimensional tensor, and if we can accept that the outcome of this fully connected layer can also be formulated or reshaped as a high-dimensional tensor, then we'll be able to decompose the weight matrix in a very efficient way, which is like this. So first, let's say the input dimension is M. If we can say that this number M can be decomposed as the product of M1 times M2 through MD, And at the same time, the output dimension n can be decomposed as n1, n2 through nd. Then we can come up with such a decomposition of the weight matrices. So what happens here is that here we see that X is a high dimensional tensor, which is the requirement because we see multiple edges coming out of it. And the outcome of this contraction is N1, N2 through Nd, which is also expected. What happens within this contraction is that we define as a chain or a train of so-called core tensors. These core tensors have either 3 modes or 4 modes, depending on if we are at the very beginning or the very last. And these core tensors are also supposed to be contracted. So here we have these edges. So the edges that connect the core tensors and the core tensors with the input that are supposed to be contracted. And with this trick, we are then able to dramatically reduce the number of parameters that are necessary for such a fully connected layer. So originally we would have this number, which is m times n. After this tensor train tensor train decomposition, we end up with a sum instead of the product with respect to the respective complexity of each of the core tensors. And it's really impressive. Back in the 2015, what they showed is that, well, with this trick, we can reduce the size of a neural network by 4 orders of magnitude, while keeping roughly the same performance. So that was back then a really groundbreaking research. And also back then it was quite difficult to follow how this computation can be implemented using the libraries that we are familiar with, such as the NumPy or TensorFlow or Torch. But the good news is that nowadays we have a very powerful API with this ISUM function that we have just seen earlier to implement, and with very few codes. So I'm going to give a very brief walkthrough of all the steps that we can undertake to implement such a tensor train layer. So the first step is that we have to define how we can reshape the input and output of this fully connected layer that is supposed to be decomposed. So let's say, for a very simple example, if we have such a mapping that we have to realize from 4096 to 16, then we can decompose it as such, 4 times the 8 to the 4 times of 2. Of course, we don't have such great numbers in reality. So the trick is that if the dimensionality of the neural network do not meet such requirement, cannot be decomposed in such a clean way, we can always pad zeros to the input and to the output until we are satisfied with this integer decomposition. And once we have figured out a way how to decompose the dimensionalities, the second step would be really to write down how this decomposition should look like using the tensor graph notation, which is what we see on the left-hand side. So what happens here is that we have input X. So we have decided we have to reshape it into as a 4-way tensor, and the core tensor is of course always 4. And the next thing we have to do is to give these connections, these edges, names. So my personal preference would be to use running alphabets. We can start from A, B, C, D through F, G, and H. So the reason that we have to name these edges is that we use these names to tell for example, the torch ISUM function how to perform this contraction, because as I mentioned earlier, there's always a unique mapping between the Einstein summation notation and the tensor graph notation. In implementing it, the only thing we have to do is to tell the torch ISUM function that we are trying to contract the tensors W1 through W4 and X, which are these 4 guys here. And based on the order, we tell the torch-Einstein function that the W1 has the dimensionality named A, E, and I. The W2 has the dimension B, F, I, J, and so on and so forth. And I tell it that after the contraction, I would like to keep the dimensions represented by N, E, F, G, and H, which are the batch dimension, and then the output dimension E, F, G, and H. And this single line of torch-Einstein is all we need to compute this very complicated tensor train layer. And the nice thing about that is that we can actually make use of the automatic differentiation in torch and also in TensorFlow, of course. And the backward pass and the step, the optimization is just exactly the same as what we would do with a normal neural network. The next thing I would like to share with you is the research directions that we have seen in the last couple of years. So the first line of research is, can we embed this tensor train trick into multiple architectures of neural networks? So right in the year 2016, practically the same group published a paper on how to perform this tensorization on convolutional neural networks. And in the year of 2017, our group and another group from Japan, we published practically at the same time at different conferences, the idea of using this tensorization on recurrent neural networks. So the difference is that from our perspective, we assumed that what we need for recurrent neural network is only a very heavy input to hidden mapping. So the only weight matrix that we have represented using the tensor train trick was on the input to hidden layer. And the Japanese group did it more thoroughly. So they also performed this kind of tensor train trick on the hidden to hidden layers of recurrent neural networks. And by the way, on the right-hand side, what we report is actually the performance, some empirical performance of this tensor train recurrent neural network. So basically, we have implemented it for the LSTM and the GRU, and for these data sets that we have tested upon, the tensor train GRU kind of outperforms the LSTM. So in comparison with a fully connected layer, we would need so many parameters, and with this trick, we only need 3,000. But honestly speaking, this is not a very fair comparison, because no one would actually use a fully connected layer to consume image data. So the experiments were performed on the video classification. So the input would be the frame of a video. A more reasonable comparison, in my opinion, would be to first feed each frame of this video clip into some convolutional neural networks and make use of the representation generated by the convolutional neural network, feed them into the recurrent neural networks. And that is I think what this paper, Sharma paper, did. So they really achieved state-of-the-art results back then in terms of classification accuracy. And our best model performed 0.8, so 81%, they achieved 85%. But if we look at the number of parameters that are necessary, they have used, unless I'm mistaken, over 6 million, at least 6 million parameters, while we only need like 3,000 parameters. So the second interesting direction would be to discover new interesting application use cases for this kind of neural networks. So in this paper, UAL, they actually took the idea from the Japanese group. So the problem that they had was they would like to perform this high order time series modeling. So the LSTM, the GRUs are not supposed to take as input only the last time step, but multiple steps prior to that. So what they need is exactly what the Japanese group proposed, a high dimensional hidden to hidden mapping with the recurrent neural networks. And then within our group, we have organized this student group, student project, led by the student Max Pittner. What we asked him to do is to take this video classification model with TensorTrain recurrent neural network to perform some kind of autonomous driving in a simulated environment. So this is actually the Euro Truck simulation video game. So quantitatively, we have shown that with this TensorTrain trick, we can outperform the classical convolutional plus recurrent neural network architecture in terms of MAE, RMC, and so on and so forth. And here we see some qualitative results, how the truck actually drives. But the rest assured, we won't see trucks driving like that on the railway in near future. This is only a student project. But another interesting thing is that we also asked them to validate that the recurrent neural net, these TensorTrain recurrent neural networks can capture the important input features, just like the convolutional recurrent neural networks would do. So the technique that we have tested is the so-called layer-wise relevance propagation. And with this trick, we're going to visualize, we are actually able to visualize which pixels are being focused on by the neural network. So I don't think those two are synchronized, but hopefully you get the idea. So the darker the color, the more focus the recurrent neural network puts on each of the pixels, which kind of helps improve the interpretability of the model. And here what we see is that it seems that the model puts a lot of effort in focusing on the tracks, which is as expected, because this is what the neural network's decision should be based upon. Of course, there are some other noises that the neural network is also looking at. So there's a third direction of research, which is can we implement other kinds of decomposition? Because with the help of the Einstein notation, with the help of the graph notation, we can actually express any kind of decomposition that we can think of. So some natural choices would be the classical CP decomposition and the Tucker decomposition. So there's actually a very interesting Python project that you can check. And the second prominent example of exploring different decomposition would be the so-called tensor ring. So that the tensor ring looks to a certain extent similar to the TensorTrain decomposition. It's just that we have two layers of core tensors, and they are somehow connected at the very left and the very right side of the core tensors. So, and this kind of the last line of research gave us the idea that probably we could figure out a way to somehow optimize the connectivity or optimize the topology of those core tensors. And just as we were thinking about the idea, there came a very interesting paper, 2020. What they propose is that, well, they were thinking in exactly the same direction. So they come up with this idea of representing the topology of the core tensors in a tensor decomposition model using adjacency matrix. So here, for example, we have a TensorTrain decomposition. The adjacency matrix would look like this, meaning that each of the tensors is only connected with its neighbor. We can also express the tensor ring or sort of tensor ring decomposition using such an adjacency matrix. And in theory, any random topology can be always represented in such an adjacency matrix. And what this paper does is to perform only the tensor decomposition. So we took that idea and proposed that, well, if we can do that, then we can actually take the, for example, the upper triangle of this adjacency matrix, vectorize it, reshape it as a vector, and optimize that as a hyperparameter, meaning that we perform two nested optimization. In the outer loop, we try to find the optimal topology of the core tensors. In the inner loop, we try to train the values within the core tensors. So we have this master thesis by Abakuku, who did quite a number of experiments on the idea of this nested optimization. So what we see on the right, on the bottom right, is that first the three plots represent the experiments on the MNIST data, Cypher10 data, and the POV15 data. And on the y-axis, we have the reported accuracy. On the x-axis, we have the performance of the tensor train neural network, the tensor ring neural network, and what he called tensor network, which is this optimized topology network. And we have multiple bounding box, and also in each group of those boxes, we have the performance by the random search, meaning that this architecture, this topology has been found using random search. In the middle, we have the topology found by Bayesian optimization. On the right-hand side, we have performance found by the evolution strategy. And because this somehow, if we directly compare this topology optimization with a tensor train, tensor ring, it may seem quite unfair because those two methods have actually much less degrees of freedom. So we also used these methods to optimize the rank of the tensor decompositions. And what we see here is actually not, so the bounding box, the variance do not come from the cross-validation or repeated experiments. They are actually all the values from the trials, from the experiments, meaning that what matters on these plots are actually the maximum. So looking at these examples, we came to the conclusion that, well, it really makes sense to perform this outer loop of optimization on the topology of the tensor decomposition. But we are also, to be very honest, we do not believe that this is a very good idea to use for daily work, for daily project, because we have to throw a lot of additional computational resource and effort into it. So because we have to train this tensorized neural network then multiple times. What we were trying to figure out with this master thesis was that, can we find some topology that can simply generalize to all kinds of problems? Can we discover some new structure of how those topology, how those core tensors are connected with each other? And one thing that we figured out is what we see on the left-hand side. So this is, I think, the best topology from the Cypher10 data set. Here we see that from the, well, just looking at it, I think it looks really similar to the tensor ring topology, but we have some connections from the input layer of the core tensors to the output core tensors. And the other interesting thing is that we have a lot of interconnections between the output core tensors. But of course, we did in the scope of this master thesis, we didn't have the time to perform some kind of ablation study to verify that it is exactly these connections that have made the difference, have improved the experiments. So for now, we're just going to leave that for further research. And with that, I would like to go to the second topic of this talk, which is about the uncertainty quantification. So like I said earlier, what we are trying to do is to combine the predictive distribution of Gaussian process with the power of representation learning by neural networks. So the Gaussian process, as we know, is a really classical classical model, simple as it is, it has actually an analytical form of the posterior distribution of the prediction. So it can be in a very clean and principled way. It can be decomposed as an epistemic uncertainty and the aleatoric uncertainty. And the entire Gaussian process is actually based on the idea that, well, or based on the assumption that, well, if two data samples are similar in the input space, then we expect them to be similar on the output space. So to a certain extent, we can see the Gaussian process as a soft version of a k-nearest neighbor model. But as we know, the bottleneck, the limitation of the Gaussian process is that in order to train a model, we have to invert the covariance matrix, and that could be really expensive if we have a large number of training samples. So as a comparison, what happens? So what is different? What is the difference between the Gaussian process as a non-parametric model to the parametric model, such as neural networks that we are used to, is that with parametric models, what we try to learn is a mapping from the feature space to the target space or output space. And with these non-parametric models, what we try to do is to map from a similarity space or the kernel space to the target space, meaning that the prediction that we make for a new data point is only depending on the similarity of this new data point to all the training samples that we have. So on this graph, which I stole from the scikit-learn, it's just a very simple visualization. So in the areas where we have observations, we have a lower we have a smaller uncertainty about the prediction, and those areas where we do not have samples, we do not have similar samples, we have a very large uncertainty. So this is what we would like to have for uncertainty quantification. The Gaussian process comes from the time when the data were really scarce. But how can Gaussian processes survive the age of big data? So in the past 20 years, I think there have been some really interesting research going on, which try to improve the scalability of the Gaussian process. And I think the majority of this research go into the direction of so-called inducing points, meaning that instead of using the entire covariance matrix or the kernel matrix, we kind of decompose this big matrix into the product of three or actually two smaller matrices. The first has the dimensionality of n and m, which is the number of training samples, and m is a hyperparameter that can be tuned that represents the subset of the training sets that I call inducing points. If I can do that, if I can decompose this full covariance matrix as the product of k and m times k m m, and the mn is actually the transpose of the first matrix, then we don't ever have to invert the entire matrix k ever again. The only thing that has to be invertible and should be inverted is this smaller matrix k and m. So from looking at from another perspective, what actually happens with the inducing points is that I use this small set of so-called inducing points as proxy. So I never directly calculate the kernel value between sample I and sample j. Instead, I calculate the kernel value between I and all the inducing points denoted as j. I calculate the kernel values between j and z. Z is, represents the inducing points, and I calculate the j with the z. So the second data point that I'm interested, I multiply these two vectors, normalize it using this invertible small covariance matrix, and that is supposed to be a very good approximation of the entire covariance matrix. And then later, following that idea, there have been some improvement claiming that, well, let's do not stick with the original training point. Let's fine tune these inducing points and let's initialize them randomly and then train them as free parameters. So I think from 2000 until 2020, there have these, at least that I'm aware of, are these four very dominating and very efficient ways to perform scalable Gaussian processes. So encouraged by this kind of research, we were asking ourselves the question, can we combine these scalable, especially the state-of-the-art scalable Gaussian processes with deep learning? Because in the industry, it is sometimes it could be really challenging to convince our customers that the deep learning really makes sense. But if we can provide our customers with the uncertainty information, telling them that the model is going to express uncertainty, the model is going to tell you, I am not certain about my prediction, that would be a really strong argument towards the customers. So the question that we ask ourselves is, how can we combine it with deep learning or with representation learning? That is not a trivial question, at least in our opinion, is that, well, in Gaussian process, we have always assumed that the input vectors are actually static. They are design matrices. They are static feature vectors. But if we want to combine Gaussian process with neural network, that would mean the neural network, the representation generated by the neural networks, are supposed to function as input to the Gaussian process. And the Gaussian process takes as input something that has to be learned, has to be adapted throughout the training. Can that really work? So we did actually 3 sets of experiments. The first experiment is, well, we decided to start small, to combine the scalable Gaussian process with the simplest representation learning task that we could think of, which is about learning lookup tables in the context of so-called collaborative filtering. In collaborative filtering, you always have this data situation where we have a matrix that describes the interaction between certain users and items, which is supposed to be a sparse matrix. And we're supposed to predict the probability that a certain user might be interested in a certain item. So a very classical way of modeling such sparse matrix is that let's learn some latent representation for each of the users and each of the items. Let's call it matrix A and matrix B. And then in order to predict or to model a certain entry in this matrix, let's call it Y and J, we simply query the ith row and the jth row from the matrices A and B respectively, put them into a function, and this function is supposed to use this piece of information to make the prediction or the model. And this function, of course, the A and B have to be learned, and also this function, if it is learnable. So this function could be as simple as an inner product, as complicated as a neural network. So, so what we are trying to do is to exactly replace this function f with a Gaussian process, meaning that the parameters of the Gaussian process and the inducing points of the Gaussian process have to be learned at the same time together with the latent representations. And the architecture that we come up with is on the right-hand side, we have these lookup tables. In each of the lookup table, we define a kernel function. We calculate the product of these 2 kernels, make use of the inducing pairs. So far, so good. And we have also shown that with our technique, we have managed to reach the state-of-the-art performance, not 100% the same as the state of the art. We are slightly worse than state of the art, but it's comparable. But the biggest challenge of this work is to show that the added value, which is the uncertainty quantification, really makes sense. How could we do that? So we have assumed that for a Gaussian process, well, if the uncertainty are really reasonable, then the Gaussian process should always assign let's say, higher uncertainty to those predictions that it has performed bad. So the worst predictions should always be associated with higher uncertainty, and the good predictions would be associated with lower uncertainty. And there we came up with a way to visualize it, which is that we kind of sort the predictions according to their uncertainty. So on the left-hand side, we have predictions of a lower uncertainty. So the most certain prediction. On the right-hand side, we have the prediction of a high uncertainty. And on the y-axis, we have the performance, in this case, RMC and MAE. So if our hypothesis would be true, then we would expect a diagonal line here, a monotonically increasing line. And to our great relief, that is exactly what we have observed. So we, meaning that this kind of uncertainty where the collaborative filtering model really does a good job assigning those smaller uncertainties to the good predictions, the higher uncertainty to the bad predictions. And of course, we have also compared our results with the state-of-the-art Bayesian GPLVM, because our line is always below that line of the GPLVM, meaning that with a certain amount of uncertainty, our model actually achieves smaller errors and better qualities. And with the success of this approach, we have moved one step further, which is about combining this Gaussian process with real deep convolutional neural networks and the recurrent neural networks. So the idea is actually quite simple. Just use some convolutional layers, generate some representation features, and put it into a Gaussian process. In comparison, here I think the most interesting part is that we were really interested in comparing, benchmarking these two variants of scalable Gaussian process. The one being the SVGP was actually the state of the art back then. The PPGP was an emerging technique in the year of 2021. So based on our experiments, we have realized that the PPGP, which is a new publication, actually outperforms the SVGP to a very satisfactory degree. And of course, on the right-hand side, we also use this technique to verify that the uncertainties are really correlated with the quality of the prediction. Here, what we compared is the performance of PPGP in blue, the SVGP in green, and the MC dropout in red. So this is about the convolutional neural network. So we have also combined the GP with the recurrent neural networks to analyze, for example, the electronic health records data. And so because these electronic health data, they have this temporal dimension, so they really record what happened to this patient throughout time. So we will need these recurrent architecture. And on the other hand, we have some basic data, static features about the patients. So the LSTM or GRU have the responsibility to perform this fusion of informations, to perform a latent representation of the entire patients, and this HI is supposed to serve as input to a Gaussian process. And the interesting thing about this work is that we realize that if we train the neural network such as it is, the neural network, the RNN plus the GP, it performed really badly. So our hypothesis is that, well, in training the scalable GP, we have to initialize the inducing points in a very random way. And these inducing points are supposed to be the bridge, the proxy of the kernel matrix. If this thing here is random, then the training becomes really difficult. It either takes many hundreds of epochs until the model starts to learn something, or the training just diverges. We have realized that it helps a lot if we can perform some pre-training. So for example, the student, the PhD student Wu, came up with a great idea of performing the the deep matrix learning, because deep matrix learning is also defined with respect to a certain similarity or kernel functions. If we have performed this deep matrix learning with exactly the same kernel function that we would use in the downstream Gaussian process, then the performance of the model can be boosted down significantly. And also on the right-hand side, we see the performance. So in this case, the PPGP, I think it also performs really, really good. And the SVGP and the MC dropout, we do not have this very nice diagonal line here anymore. I think with that, I would like to conclude the presentation for today. And thank you very, very much for your attention. Thank you. If there's any question, I would be happy to take them.
Dr. Yang, for your questions. So if there's any questions from the audience here or from anyone online, please raise your hands.
Thank you very much for the talk. Regarding the first part, so how do these tensorization methods compare with pruning methods?